and welcome to this lecture in this module of concrete engineering and technology, where we are talking of diverse subjects ranging from fundamentals of concrete, proportioning of concrete mixes, stages in concrete construction, special concretes, mechanisms of deterioration, reinforcement in concrete structures and maintenance. The idea basically being to have a bird's eye view of the different aspects of concrete and concrete construction, including maintenance, that a modern day concrete engineer is expected to be familiar with. In addition to the topics that we have covered here, there are some topics which are of special interest to concrete engineers and do not really fall under the ambit of traditional concrete engineering. But having said that, some understanding of these topics is absolutely integral and vital to ensure quality concrete construction. And today we will focus on two such subjects, one of them being grouting. The second will be special formworks. So, we know what formwork is, and we will be talking about some special issues related to formworks, developments in the formwork engineering, if you want to call it, that have taken place in the last couple of years. So, now starting the discussion with grouting, what is a grout? It is defined, or it can be defined as a fluid material designed to be introduced into a cavity for the purpose of filling it. Further, the material should subsequently harden and prevent ingress of deleterious material into the cavity. So, in a manner of speaking, when the dentist fills the cavity with some material, it is also grouting, except that in most cases he does not apply any pressure, or the pressure applied is limited to pressure applied by the hand. That in our kind of work, that is in the kind of civil engineering that we are talking about, it will be basically application of a mortar. That is what we do when we apply mortar to a surface of brickwork or concrete and so on. However, when it is grouting, typically there is pressure associated with it. We fill the cavity with the fluid material under pressure, and that material hardens in the cavity. In the context of cement concrete, grout may be considered to be made of water, cement, sand, admixtures, fly ash and some fine gravel. Now, fly ash is a mineral admixture, it can be used, it may not be used. When we say admixtures here, we are typically referring to chemical admixtures, which could be water reducing agents, accelerators at times and so on. And at times, other than the sand, which is having a certain sieve size, we could use slightly bigger particles than that and still use it in grouting. Now, coming to the applications of cement grouts as far as civil engineering is concerned, one of them is in pre-stressed concrete, the other is in pre-placed aggregate concrete, and the third is crack filling in repair works, besides several other applications which are not traditionally or which are not really in the ambit of concrete engineering. Coming to pre-stressed concrete, we have talked about it sometimes, that there are two kinds of pre-stressing in concrete. One is pre-tensioned, where tension is applied to tendons before casting the concrete, and after the concrete is placed, it is allowed to harden, and when it attains sufficient strength, the strands are released. That is, the tension in the strands is then transferred from the steel to the concrete, or at least a part of it is transferred to the concrete, and by that token the tension in the steel tendons reduces to some extent. Coming to post tension systems, in this case, after the concrete is placed, it has hardened and has attained a minimum compressive strength, tendons are placed in pre-placed ducts and tensioned. So, basically the ducts are already in place at the time when the concrete is cast. The pre-compression is transmitted from the steel to concrete by a suitable anchorage device at the end blocks. So, this is the principle of post tensioned concrete, and in the latter case, which is post tension systems, the remaining space in the duct is filled with grout at times. So, basically what is happening is that if we have a duct, we have a certain amount of space which gets occupied by the tendons, and the remaining space here, this space is what we seek to fill with grout. As far as the post tensioning method is concerned, the ducts are left in position at the time of casting the concrete. Reinforcing tendons are placed in the duct after the concrete has been cast. The ducts prevent contact between the concrete and the tendons during the tensioning. Unlike pre-tensioning, the tendons are pulled with reaction against the hardened concrete, and that is why we need a certain amount of strength in the concrete before the tensioning can be done. In cases when the ducts are filled with grout, the whole system is known as bonded post tensioning, and that is what we talked about in the previous sketch that we made. In the case of unbonded post tensioning, the ducts are not grouted and the tendon is held in tension solely by the end anchorages. And in this context, I would like you to look up the systems that have been used in external pre-stressing. Now, external pre-stressing is a completely different thought process compared to normal pre-stressing in terms of pre-tension and post-tension that we talked about just now, in the sense that these tendons are placed outside the member which is being pre-compressed. We have talked about it a little bit when we talk about some discussion on external pre-stressing would take place when we talk about repair systems. This is one of the methods that is often used as a rehabilitation tool. Now, coming to the performance and properties of a cement grout. After all, when we are grouting a duct, trying to fill the space in the duct which is left after the tendons have been placed, we need to have a certain performance. We need to have a grout which fulfills certain criteria. One of them obviously is the ease of mixing. The material should be such that it can be easily mixed. Secondly, it should be flowable. Unless the grout is flowable, it will be difficult to push the grout into the duct. And please remember that these ducts are often several meters long. So, if we have a concrete girder which is, let us say, 20 meters long, what we would expect is that the grouting operation, once it starts here, the grout would be expected to flow through a reasonable distance. May not be the entire 20 meters, because we could be trying to grout through multiple locations, but still there would be a substantial distance involved for the grout to be able to flow. And that is why we need to have flowable grout. At the same time, if the grout is not having a flowing consistency, it would be difficult to even use normal pumps in the construction process. Another property for the grout which would be of interest to us is the setting time. Like all concrete construction, the grout, once it is reached its final location, we would like the system to set, and therefore, the setting time is of great importance as far as grouts are concerned. Segregation or bleeding, especially under pressure. Grout, like any cementitious composite that we have been talking about, tends to bleed. That is, water tends to separate out from the constituent materials, and this tendency for segregation is sometimes enhanced when the material is being moved under pressure. So, we have to be able to study, or we should have a benchmark on what is an acceptable level of bleeding. Shrinkage compensation. Again, grouts, because they do not have coarse aggregate, proportionately speaking, the volumes of cement are much higher, and therefore, there is a tendency for the grouts to shrink, unless special measures are taken to add admixtures and so on to make and design shrinkage compensation grouts, that is non-shrink grouts which do not have which do not shrink. So, therefore, we need tests which will determine the amount of shrinkage that a grout undergoes and have specifications which will say that only a certain amount of shrinkage is acceptable. Durability and strength are obvious requirements in any cement based construction, and grouting in post tension concrete ducts is no exception. We need or we may need to specify that the grout that we use attains a certain strength at a certain point in time, whether it is 28 days or 7 days or 3 days or whatever the time be. Corrosion inhibition. Remember that the function of the grout is that it should surround the tendon, and one of the purpose of having a cementitious grout is to protect this tendon against corrosion. Therefore, effort is sometimes made to use a corrosion inhibitor. Nitrites are one example of known corrosion inhibitors, and they are used sometimes in the grout in order to impart a greater corrosion resistance to the tendons. Resistance to chemical attack is an important issue, especially if we are dealing with chemical grouts or resin, especially if we are dealing with resin based grouts rather than cementitious grouts. As far as specifications are concerned, for example, in India, IS 1343 mentions some of the properties that are required as far as grouting in pre-stressed concrete construction is concerned in sections 12.3.1 and 12.3.2. As far as ASTM standards are concerned, some examples or some performance parameters are that the setting time should be more than 3 hours, but less than 12 hours. The strength of the grout tested with 50 mm specimens at 7 days is required to be at least 21 MPa, and at 28 days is 35 MPa. Similarly, the volume change, there are specifications on how much is the acceptable volume change at 28 days. It should be remembered that when it comes to setting time or grout strength or volume change, these tests have to be specially designed, and I would request you to please refer and read these standards in order to be able to understand and appreciate the tests completely. It is important to note how the setting time of a grout is determined and how it is different from that of the setting time of cement. In this connection, you would also recall that we have talked about the setting time of concrete, and that again was a very special method, not really the same as testing the setting time of cement, but in principle the same, that is based on penetration resistance. And the same is the story with strength and volume change as far as grouts are concerned. Now, this here is an illustrative example taken from one of the references. So, the pre-stressed tendons are not necessarily straight, and they could follow a profile which is something like this. And these here are vent holes which help us remove the air from the duct while the grout is being moved in. And then of course, we can try to take pictures of cross sections at different places and try to see whether or not the duct has been fully filled with grout. This here is an illustrative example of what is the kind of equipment that is used. We have a mixing hopper here where the material is being mixed. Through a screen, the material is fed into a hopper and then to a pump, and finally to the inlet where the grout is transferred from the mechanical system here to the concrete duct. This here is another example where we can see that there is a person involved at the end of it carrying out the grouting operation, and the quality of grouting done is very much related to the skill of the person involved. So, there is no denying that workmanship is one of the very important determinants as far as quality of grouting is concerned. As far as the operation in superstructure tendons is concerned, grouting is done through a series of pre-decided inlets. Grout should be injected steadily and consistently into the first inlet. So, we cannot have intermittent supply of grout. We cannot just grout a little bit, stop and then start grouting again. That unnecessarily leads to air pockets in the grouting systems, and that is very highly undesirable. So, we must ensure that the grouting is carried out steadily and consistently once the operation has started. When a consistent flow is seen through the first intermediate outlet, so there is a series of outlets and we are trying to pump the grout into the first outlet, and as the grout emerges in the second outlet or the first intermediate outlet, the first outlet can be closed, and then we use the second point as the inlet to push the grout further, and this process is carried on till all the grouting is completed. As we say here, injection is continued until all intermediate outlets have been closed. As far as pre-grouting operations for quality assurance of the whole program is concerned, even before the tendons are placed, so what happens is that if we have a concrete beam and we have this duct where we want to place the pre-stressing tendons later on, at the time of casting the concrete here, vibrating it and all that kind of process, these ducts may get deformed, and if these ducts deform during the concreting process, it will become difficult for the tendons to be placed. And this is the kind of check which is being done here, that is, even before the tendons are placed, clearance in the duct should be checked. It should be ensured that the tendons can be easily placed in the duct. Prior to the grouting, tendon ducts, grout inlets and outlets and anchors, whatever they are, should be examined for any debris and or water. They need to be removed to avoid blockages and or dilution of the grout. All connections from the grout hose to the inlet and outlet should be airtight and free from dirt. Ducts should be tested using compressed air to ensure that there are no leaks in duct connections or joints. Now, how do we do that? One way of doing it is to pressurize the duct system to a certain level and then have an acceptable loss in pressure at a certain time. See, what will happen is that if we have a duct system here, which is surrounded by concrete and so on, it obviously has some tendons in it, and this void has to be filled. There will be some obvious leaks in the ducts, but these leaks in the duct and so on cannot exceed a certain value. And in order to determine whether there is any problem in that connection, if we pressurize this air here, if we pressurize this system here, what we will get over time is that the pressure will drop. Now, this drop, if it is too much, if this drop is unacceptable, then of course, we need to carry out repair work on the duct system before we do the grouting. Therefore, what we need to do is to say that, okay, we will carry out the test for a certain period of time, and the pressure drop during that time should not exceed a certain predetermined or an acceptable level. So, this is how we can ensure an airtight duct system. It is not airtight in the scientific sense of the word, but it is airtight in an engineering sense of the word. As far as the quality of grouting is concerned, very high grouting pressures could lead to failures of ducts and cracking in concrete. Flushing in a partially completed grouting operation is generally not preferred. We cannot stop the grouting operation and then try to flush it out and then commence again, because of the obvious reason that the flushing may not ensure all the removal of grout, and that could become a problem if we want to go back again and grout the system. Before the grouting, of course, the ducts need to be flushed and cleaned, as we discussed. If of course, the flow time, that is the flowability of the grout, which is typically measured using normal funnels, which could be V funnels, and the specifications are given in terms of the acceptable flow time. If the flow time exceeds the limit, that is, the grout is more viscous than is acceptable, the test can be repeated once, but no ad hoc measures such as addition or reduction of water or chemical admixture should be resorted to. Even though the grouting operation is carried out in the field engineers should not resort to ad hoc measures. A grout designed for a certain specification, if it is not performing in the field for whatever reason, it could be temperature, it could be compatibility of materials, it could be change in materials and so on, a proper study should be carried out, and then only the grouting operation should be continued, because ad hoc measures could lead to problems later on in the maintenance of the structure. Complete grouting should be ensured using volume balance or any other method. After the grout has set, the tendon should be inspected, voids should be measured and filled using vacuum grouting or whatever other method is available. So, basically there is very little that we can do once we are grouting a post tension pre-stressed concrete tendon. We do not know if all the void, if all the space in the duct which was supposed to be occupied by the grout has been occupied by the grout, other than by doing some kind of volume balance or carrying out non-destructive tests, which could be carried out while the grouting operation is being carried on or after the grout has set, and then we look for pockets of air. As far as bleeding is concerned, bleed water appears at the surface while the grout is still plastic, and in a grouting application this water cannot escape. There is no way that we can take it out. It will therefore create a zone of weakness in the duct wherever it accumulates. As we have seen in the case of concrete, bleeding is related to the water content and the water cement ratio of the mix, and of course improper or incomplete mixing. Similarly, shrinkage in grouts can also give rise to spaces in the duct which can allow ingress of deleterious substances, and that is why we need to ensure that grouts meet requirements in terms of bleeding and shrinkage, in addition to whatever other criteria we may choose. So far we have discussed the issue of grouting in post tensioned pre-stressed concrete tendons. The principle of grouting is the same, but now let us spend a little bit of time talking about grouting in a pre-placed aggregate concrete system. Now, as the name suggests, pre-placed aggregate concrete refers to a situation where wherever we want the concrete, instead of trying to cast the concrete there, we place the aggregate first and then try to fill this space with cement mortar. So, in engineering terms, this is what is called pre-placed aggregate concrete, because at the end of it what we get is a concrete system which comprises of coarse aggregates embedded in mortar, except that they were not mixed to begin with, only the aggregate was placed first and the mortar was pumped in at a later point in time. Now, when we are considering the requirements of the grouting material, that is the mortar that we use to fill this system, the principles of grouting would apply. That is, we would be interested to know what is the size of the coarse aggregate and the particle size distribution, which will determine the characteristics of the void space. If we have very small particles, the amount of void space will be different compared to having larger particles. In the case of concrete construction, we deal with particle sizes which could be as much as 20 mm or 25 mm or sometimes even 40 mm. Sand, on the other hand, is defined as material which is lower than about say 4.75 mm. So, it is not so easy to decide the characteristics of the grout unless we know what is the kind of void system that we are dealing with, which is related to the maximum size and the particle size distribution of the aggregates that we have used. Now, having said that, for a given system, we need to have a certain flowability of the grout, and that is again very similar to the kind of flowability that we were talking about when we talked of grouting in the case of ducts in post-tension concrete construction. As far as the construction is concerned, in pre-placed aggregate concrete, where do we start the grouting process? Whether we take a pipe and just let the grout flow under gravity, filling the spaces here, or we try to push the grout under pressure from below. If we are pushing the grout from the top, there is a possibility that the grout might not reach all the spaces, whereas if we are pushing it from the bottom, the chances are that we would be able to accomplish a higher filling, even though it is more difficult to do. So, there are issues related to pre-placed aggregate concrete, but in this limited discussion that we have, I am just trying to show it as an illustrative example related to grouting. As far as the subject is concerned, there is a lot more to study than of course this. Now, let me just quickly go over the third example of grouting that we have chosen to talk about, that is grouting for filling of cracks in a repair rehabilitation strategy. So, if we look at a concrete crack, we could typically see something like this. The cracks could be wider, narrower at the surface and so on. What we often do not know is how deep the cracks are, and therefore, we do not have any idea as far as how much volume of the mortar or the grout will be required to fill these cracks. How this filling process works is shown here in this picture. We see that the cracks are sealed. These are nipples which are left in place and used for the grouting operation. So, once we start filling here, the grout starts flowing inside the material, inside the concrete, and then appears in neighboring nipples. We close those nipples and start from different places cracking system, ensuring that the entire crack system has been filled with the grout. So, finally, we have a system which looks a little ugly because of this kind of patchwork along the cracks, and that needs to be painted. Obviously, in this case as well, depending on the width of the cracks, we would need to have different specifications for the flowability of the grouts that we can deal with. A grout which is good to flow into a crack width of this magnitude will not suffice if we are trying to fill cracks of this magnitude. So, these are the kind of balancing acts that an engineer at site needs to be playing. In order to grout a cracked system, one has to decide what is the kind of specifications, what is the kind of parameters that you would use to control the quality or control the performance of your grout. Now, with this discussion, we come to a close on the first part of our discussion today, which was on grouting. Now, continuing our discussion, we talk a little bit about special formworks. Now, before we talk of special formworks, we must know what is formwork, or look at the formwork definition and the functions once again. Formwork really refers to any structure which is put in place before concrete is placed, in order that the concrete that is cast inside is given a certain shape. Now, therefore, this structure, which is the temporary structure, that is the formwork which is removed after the concrete has gained sufficient strength, should be such that it is able to withstand the normal loads of construction without impairing the properties of concrete. Even though it is a temporary system, it is an important system to ensure that the final product of concrete, the member or the structure that we are talking about, has a good quality. It is important that the formwork that we have is of good quality, and therefore, this system also needs to be appropriately designed to ensure that whatever we expect from it in terms of shape, size, tolerances and so on is met. Now, reiterating these requirements, it should be able to sustain the loads during construction, and that is more or less similar to that of structural design. The kind of loads that could be are concrete weight and pressure, the live load of equipment, that is vibrators and so on, personnel, that is people who will be moving around on the formwork or on the concrete during construction. You can think in terms of a slab while it is being cast. Not only there will be a dead weight of the concrete of the slab, but also there will be some vibrators and other equipment which will be on it. There will be people moving around to ensure that the concrete is properly cast, vibrated, compacted and so on. And finally, there will be people moving around even after that for curing, inspection and all those kind of purposes, while the concrete is still not strong enough. Once it is strong enough, it has sufficient strength, the formwork needs to be removed, and how long that takes is a different matter. It depends on the kind of properties of the concrete, what is the kind of strength development and so on. The formwork should be free from leaks, that is the joints in the plates of the formwork, whether they are made of timber or whether they are made of plywood or steel, the joints should be free from leaks. They should be properly sealed, because leaks in the formwork are the major source for honeycombs, and honeycombs is something which is highly deleterious and has a direct bearing on the durability of the structure. Should be true in shape. Unless the formwork is true in shape, there is no way that we can have a concrete structure which will be true in shape. So, if a wall has to be vertical or the slab has to be flat, then it is important that the formwork has the right kind of tolerances. That is, those plates are not having undulations, because once those plates or panels have undulations, the concrete that is cast against them will obviously reflect that. The formwork should be clean, lest it discolor the concrete surface or impart properties which are not desirable from aesthetics or any other point of view. Now, this is the general discussion on any kind of formwork. We must also remember that once the concrete is cast against formwork, that is, if we have this as my formwork panel against which some concrete has been cast, and this concrete has reinforcement, then this distance here, the concrete here is really the cover concrete. We must remember that depending on whatever happens at the formwork level or in the formwork, the properties of the concrete in this portion here are the ones that are likely to change most. Formwork is not likely to affect the properties of main body concrete, but it has a direct bearing on the properties of cover concrete, and the properties of cover concrete are a very important issue when we are talking in terms of durability of concrete structures. Conversely speaking, therefore, if we want durable structures, we need to have good quality cover concrete, and in order to ensure good quality cover concrete, we need to have good quality formwork, and that is what gives rise to special formworks and a whole lot of discussion relating to that aspect. Some of it which we will briefly discuss from this point onwards. Now, coming to special formworks, let us first talk in terms of what is called permanent formwork. Temporary formwork is the normal formwork which is removed after the concrete has achieved sufficient strength. Permanent formwork, on the other hand, contains the placed concrete, molds it to the required dimension and remains in place for the life of the structure. That is, this formwork is not removed after the concrete has been cast, it becomes part of the concrete member itself. Now, in this there could be two kinds of permanent formworks, what can be called a participating formwork, and one is participating formwork, in which case a predetermined contribution is made to the strength of the structure. That is, the formwork is part of the structural behavior as far as the concrete member is concerned. And of course, then we can have a non-participating formwork where it makes no contribution to the strength, but provides only additional benefits in terms of durability, finish and insulation and all that kind of stuff. Now, let me explain this issue a little bit again. Consider a column with the reinforcement and whatever it is. If this was the normal concrete that we use, what we would do normally is to cast this column against panels which could be made of plywood or steel, and we remove these plates. This is the normal construction that we would do. As against that, if the panels were now such that if these panels were now such that they would remain as a part of the column and not removed, then we can expect two things. One is that this panel, depending on its thickness, the material, the kind of structural properties and so on, these panels are considered when we talk in terms of the load carrying action or the load bearing action of this column is concerned. The other option, of course, the other possibility, of course, is that these panels are not considered when we are talking in terms of the load carrying mechanism of the column, and the same thing really holds for the beams as well. So, we have participating permanent formwork and non-participating permanent formwork. That formwork differs from regular formwork in the sense that it becomes a permanent part of the structure and is not struck off after the concrete has hardened and gained sufficient strength. Now, advantages of using this kind of formwork system is that it could contribute to some kind of reduction in cost and time, because we do not have to wait for striking of the formwork. The entire process as far as striking of the formwork is simply not there, and once the concrete has been cast, we can proceed with the other operations. It eliminates the need for doing any kind of false work, reduces the skill level needed at site, because formwork is a skilled operation. Erecting the formwork is a skilled operation. Most of these panels that are made are precast or prefabricated panels which are used in the construction, and therefore, the skill level required in the erection is different and of a much smaller magnitude compared to erecting normal formworks. Increases the potential for standardization and repetition. Now, this is something which is very important as far as civil engineering construction is concerned, that if we have standardization in sizes, then it becomes a lot easier for all engineers to have certain discipline as far as quality control is concerned. Flexibility in concrete construction is, of course, the principal reason why concrete is a popular material, but if we have some kind of standardization as far as sizes and so on is concerned, it will help in ensuring better quality control. Speeds up the erection time, eliminates the need to strike formwork and false work, improves the curing of concrete and reduces the shrinkage cracks. Obviously, the purpose of curing is to ensure that the water from the concrete does not escape into the atmosphere, and if we have permanent formwork, then what we have ensured is that the passage of water to the atmosphere becomes all that much more difficult. Ensures adequate cover and associated benefits. As we try to draw in the previous picture, having permanent formwork effectively adds to the cover thickness. Now, depending on how a designer views the cover thickness, we have a reinforcing bar here, we have normal concrete up to this point, and this is our traditional cover concrete. And if beyond this point we have a permanent formwork of a certain amount of thickness, now whether this thickness here of the permanent formwork is to be counted towards the cover thickness or not is a decision which the designer has to take. It has to have certain sanction as far as specifications and design methods is concerned, but nonetheless it should be borne in mind that at the end of it, this permanent formwork is also contributing to protecting this reinforcement from the environment outside. Permanent formworks can be used to provide decorative finished surfaces, because this side of the panel is not cast in situ. It can be used to provide decorative finished surfaces, because the outside of the panel we can have designs, we can have colors, whatever we want. Now, let me talk about timber or plywood, which is one of the most common materials used for normal formwork, is not really suited for permanent formwork construction, because it absorbs water, swells, and may rot over a period of time and result in unacceptable odor. So, these are the kind of problems that normal plywood applications would have if we were to allow them to be part of the concrete structure, and that is why we cannot have them, which gives us a pointer as to what are the kind of materials that we are looking for when we are talking in terms of permanent formwork. The materials should be such that they have sufficient strength to carry the loads, including the hydrostatic pressure of concrete that may act. They must have sufficient durability. They could be therefore made of high density fiber reinforced sheets. It could be cement based, fiber reinforced, rigid sheet. Fibers are predominantly reinforced in one direction to optimize load to span characteristics in those panels, and there should be a compatibility of the formwork panels with the concrete itself. With this discussion in mind, let us take a look at some of the examples. Here we are talking in terms of an example where a rigid plastic sheet is being used as a permanent formwork, and we can see normal reinforcement here and these kind of anchors which are going to help the formwork remain as part of the concrete construction. So, as far as rigid plastic sheets are concerned, they are lightweight and durable. It is vulnerable, however, to damage from immersion or internal vibrators. So, if we are casting the concrete against this kind of formwork and we use internal vibrators, those vibrators will obviously impact the formwork sheets as well, and therefore, unless the sheets are strong enough to be able to withstand that vibrator impact, the formwork sheets are likely to be damaged, and that is something which we need to be careful about, either by choosing the concrete that we use properly. We could use self compacting kind of concretes which do not require internal vibrators and then use these sheets, or we place something to ensure that the joints and edges of the rigid plastic sheet are properly sealed with the tapes. Here is another example where fiber reinforced concrete panels are used as permanent formwork. So, here we can see these panels which have been placed between pre-stressed girders during reinforced concrete construction. Now, this picture here shows the fabrication of such a panel, and we can see these kind of a wire mesh or a fiber mesh, and normal cement mortar is being placed and the panel is being fabricated. Of course, there is a possibility that there can be several layers of this fabric to reinforce the permanent formwork panel. Here is an example of erection of permanent formwork, and we can see how the panels are being placed in position. Other materials as far as permanent formwork is concerned could be galvanized iron sheets, which are strong and readily available in different shapes. corrosion over a long time could be a problem in the case of using sheets, and therefore, we need to be careful as to what kind of tests are carried out to ensure the durability of these sheets. Concrete panels which are precast, highly compatible with concrete construction. We have the flexibility in shape and are excellent advantages in that context. However, these concrete panels are prone to cracking and need to be reinforced with fibers and fabric like we saw in the previous pictures. And here is an example of these panels being erected and placed in position for the concrete to be cast. And we have glass fiber reinforced concrete panels, in which case we have a rich mortar with alkali resistant glass fibers sprayed into a single mold, and this spraying business reminds us of shotcrete and fiber reinforced shotcrete that we have done earlier, and panels made in this manner can be used as permanent formwork, much in the manner as being shown here. Indeed, when we are trying to work in terms of permanent formwork panels, there have to be tests in order to ensure that those panels can indeed take the kind of load that will act on them during construction and during the early stages when the concrete has not developed full strength. As far as participating formworks is concerned, where the formwork is also expected to be a part of the load bearing action of the concrete member, we need to have tests to figure out or to understand the structural behavior of these columns. And these pictures here show two tests, a static test kind of a situation here to figure out or to understand how the panel deforms under the application of load. And of course, there can also be a situation of, and other than a static test, there can also be a drop weight type of an impact setup, which is shown in the picture to the right, where we try to understand the impact resistance of a panel. Now, coming to another category of formwork which is not necessarily permanent, we have absorbing formwork, and in this case we use them to get better surface finish and quality enhancement of the cover concrete. These formworks have a layer of absorbing material on the surface of normal formwork. So, what we really have is a panel of normal formwork on which an absorbing layer is fixed, and then the concrete is cast. So, basically, instead of casting this concrete against this normal formwork panel, an absorbing layer is introduced in between, which is attached to the formwork and is removed along with the formwork. Like the formwork, this absorbing layer also has certain number of repetition cycles that it can be reused. Now, this absorbing layer allows the air and water from the concrete to escape, and this provides a better finish and higher durability for the cover concrete. So, what is happening is that if we are able to get the water in this part of concrete, which is the cover concrete, because we have reinforcing bar somewhere here, if we are able to get the water of this layer out from the system, it will enhance the quality of the cover concrete. It will reduce the water cement ratio in that region, and that is precisely what absorbing formwork does. Water from this region is absorbed by this formwork, and therefore, we get a cover concrete which has a water cement ratio which is lower than the water cement ratio in the main body concrete, and that enhances the durability of the structure which is made with this kind of absorbing formwork. Now, what kind of absorbing material is good, what kind of absorbing material can be used, how many times it can be recycled, what is the economics of the whole process is a detailed subject which cannot be obviously covered when we are just trying to give a bird's eye view of a special formwork. And that we can leave to someone who is interested to do that kind of reading. Now, coming to the close of our discussion, let us try to take some questions which we can talk about later on. We could carry out a comparative study of some of the specifications for grouting materials and performance evaluation of grouts. So, please remember that the grouting materials and the grout are different things. The grouting materials can have different tests, different specifications, and the grout again can have different tests and different specifications. And what we are talking about here is to carry out a comparative study of some of the specifications in this regard. We could list tests which are required to be carried out for the evaluation of the grouts and grouting materials. We could talk in terms of reading case studies for application of preplaced aggregate concrete and crack injection grouting that we saw briefly today. On the issue of formworks, I would request you to study available literature on the design of formwork systems. Very often the durability of concrete structures is compromised because the temporary formwork system is not appropriately designed. We could make a list of performance parameters for the formwork systems and list what are the issues that formwork design should address when dealing with high flowability concretes, which is becoming more and more increasingly used in concrete construction. Now, we could read case studies for application of permanent absorbing formworks and make a list of commercially available materials that can be used in making absorbing formwork, or for that matter some of the materials that is available to be used as permanent formwork. Try to study the technical details as well as the economics of their use and their implications in terms of the durability of concrete which is finally achieved. With that, we come to an end of the discussion today. Thank you.